Hello, and welcome to today's webcast, Accelerating Lead Identification Through Paramagnetic Bead Purification Technology, presented and sponsored by GenScript. My name is Lauren Berry, and I will be your moderator for today's webinar. Before we begin, let me explain how you can participate in today's presentation. First, if at any time you're having audio difficulties or slides are not advancing, simply hit your F5 key to refresh your webcast console. If you have any technical difficulties during today's session, please press the Help button on your player console to receive assistance in solving common issues. This webinar technology allows you to resize the presentation by clicking the Maximize icon or by dragging the lower right corner to enlarge the window. We welcome your questions during today's event. In order to submit your questions to today's presenters, please type your question into the question window on the left-hand side of your screen and then hit the Submit button. We'll be answering as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time and we'll add them to the queue. Please also be aware that today's session is being recorded and will be available within the next day for you to review. You'll be notified by email when the archive is available. On your console, the GenScript website is hot linked in the resources list. So if you want to visit their website during this webcast, you can click the link in the resources tab and a new window will open up. This will not take you out of the webinar. Let me now introduce today's presenters. John Kawuya, the director at Amgen, and Jyoti Kinghorn, product manager of GenScript Inc. Now over to our presenters to begin the presentation.
Okay, I'm going to present accelerating lead identification through paramagnetic bead purification technology as shown in the title here. So the overview here of this presentation is as follows, as you can read down here. What are paramagnetic beads? How are they synthesized? And how are they applied in the magnetic bead purification of antibodies? And then I'll follow it up with the different scales of protein purification in terms of antibodies, starting from the small and the medium scale using cell cultures and single vessels. And then I'll go through the micro scale, the high throughput systems using a robotic system. That will be followed by the small scale purifications, also a high throughput system, automated, semi-automated. And then finally, end up with a large scale, which now goes up to the large wave bags around 25 to 30 liters. So paramagnets are metal alloys which orient themselves towards the magnetic field when they're brought very close to the magnet. Okay, that is a permanent magnet. When you withdraw that magnet, the molecular entities of these paramagnets just go in a random orientation, as you can see on the left-hand side. So they are made by co-precipitation of these various compounds, which I will not go through in detail. And as a mixture of these under different conditions, you find a co-precipitation of these molecules, which are called the paramagnets. And those can be made in different shapes. Usually in the magnetic beads, they make them in the form of balls, as you can see, sphericals, and eventually conjugated with the agarose as a surface. And from the surface of that agarose, that's where we attach protein A, the ligand for the antibodies. So the reason why we're going into this is that purification of antibodies is a labor-intensive process. Costs a lot of money because of the upstream clearance before the samples are loaded on the column in terms of the traditional methods. But with the paramagnetic beads, we can go directly into the crude cell culture with the cells and then just load the samples on the beads, separate the beads with the magnet, and what we have is our ligand on the beads and just wash the beads and eventually take off the protein. So the bottleneck in protein purification or antibody purification is usually the purification step. So the bottleneck in terms of obtaining purified antibodies is the purification step, as you can see in this figure. Cloning usually can run as many as 1,000 molecules in parallel. expression around 100 to 500, but the purification takes just a very, very small number of samples. So you just block the whole system through purification again. So these are the pros and the cons of protein purification by either column versus magnetic beads. With the protein purified on magnetic beads, you get a 36-fold cycle time reduction. You have no centrifugation, no filtration. You reduce the cost of labor in terms of the amount of people you put on the centrifugation and filtration. One person can do the whole process. Okay. The cons for the magnetic beads is that there is a lack of track record. The cost of beads is still very high, and there is a lot of lack of magnetic devices for capturing beads after putting them in the cell cultures. So now I'll show you how we can do this. In our organization here, we have started engineering devices which can capture beads from cell cultures. I'll start with the small scale, single small scale vessels. And here we use just commercial available magnetic rods, which are retractable. As I said, when you put magnetic beads into very close to the paramagnetic beads, you induce a magnetic effect so that the beads reattach to the magnet. Once you withdraw that field of permanent magnet, the beads will just fall off the magnetic rod. And so these instruments are available on the internet. You can find them. They are called the retrievable baton magnetic rods. Okay. In our organization, we have built a new system which is also autoclavable. The other ones are not, and they are the magnet and the sleeve all together. Here we have a separate magnet, and the sleeve is also paramagnetic in the sense that it becomes magnetized only after the magnetic rod is inserted in there. So this is the general process. The cells are grown and the beads are added 12 to 24 hours before harvest or the end of expression. Then once the beads have been there, say overnight, you come with this magnetic rod with a magnet inside and insert it into the bottle and shaking a little bit. It takes about 15 to 20 seconds, and you're able to retrieve all the beads from 2.5 to 5 liters. The response is very strong. So once you get all the beads on the rod, you just pull out the rod, and then the same thing can be done with the cells which are grown in 15 mil cell cultures. Okay, as you can see over here, addition of beads into the cell culture does not impact the quality of the product. As you can see in the analytical size exclusion data on the graphs, at the same time, you can see that the cell viability is not affected one or the other, plus or minus beads. So this slide just shows you how you insert the beads, so the magnetic rod into the cell culture, which has got the beads in the next slide, the dark one there. And you can see in the right slide, we have the beads pulled out, and the cell culture attains the same colors before the beads were added. This is really a follow-up, but what it shows here is that on the graph, you can see that the protein was purified, was free of aggregates, very low aggregation levels, and the yields were quite high, as you can see on the scale. So the beads now can be washed with what we call these magnetic traps, and there are two methods. You can put it in a raw bottle after you have added in this the wash buffers. Alternatively, you can just shake the bottle and then just align it very close to this magnetic trap, which was custom made. And then we just tilt and just get rid of the liquid and retain the beads. So this is an SDS page showing the non-reduced PSDS page on the left-hand side. You can see the area weight, starting with the feed, which was the lot of product, as you can see at the high molecular weight mark. There, the flow-through shows that all the protein was captured. And then after washing, It shows very much the early weight, and we ran it on the other gel, which is the native without SDS, and you can see that the samples was quite clean. Mass spectrometer, you can see we just see virtually one spike here, and the analytical accuracy, of course, is also very clean here. Purity was around 97%. So now that is from a single vessel. Now we have also a format where we can purify at least at 288 molecules in an hour. This is at a very small scale. This scale is important in screening engineered molecules to find the best leads for scale-up. So we use the Kingfisher, which is from Thermo Fisher. And this instrument, we have found it very efficient, at least on the market. This is the best high throughput system. We have adopted it from its application DNA. I'll not go too much in detail. The information on how the system works is on the internet. You can find it out there. So again, this diagram just summarizes the mechanics of the Kingfisher. So the first thing is to get the beads into the 96 microtiter plate. We bought this magnetic bead mixer or paramagnetic bead mixer. It's really proud from GNP Scientific in San Diego. So use that to get a homogeneous population of beads as they continue to get mixed. You bring in your multi-channel pipetta and then transfer the beads into the. This ensures that you have uniform distribution of beads from well to well. And now there are two ways of purifying the beads with this system. You can either do it offline from the Kingfisher by manually getting a magnetic comb, and that magnetic comb, which is can be really inserted into a sleeve. All these are sold by online as well. And you use that sleeve to insert into the 96 microtiter plate, whereby you'll be able to capture the beads without having the beads sticking directly to the magnetic comb. And the separation just occurs by withdrawing the magnetic, the magnetic comb, and the beads will just come off and they are transferred into the next plate. So you move from plate to plate, and after 3-4 cycles of fresh buffer, you end up with a very pure protein, and this usually takes about 15 minutes. Surprisingly, it is faster than the Kingfisher. So over here now, what we show that we can run multiple plates on this system. In the day, we can purify at least over 3,000 molecules. So this just shows you very briefly on how purification can be done on the Kingfisher with all the buffers put in. I'll not go too much in detail here. Again, these things you can get all the details on the slides. But this is the way the magnetic plates are moving on the carousel on this system. So we have also been able to purify up to 6,912 antibodies in 24 hours. So these are the results of the molecules after being purified on the Kingfisher, and they were done side by side with the standard. These molecules were done on the Thermo Fisher, and then we had another system which we used to purify the same proteins on the purification column purification methods. So these are the results showing the caliper analysis of the molecules which are purified from the Kingfisher. Overall, the quality was very good. So the exclusion data, you can see it was around 98%, and the caliper showed that that's shown you very much single bands. So now, what are we doing with all these 96 molecules, 192 molecules per hour? This is really a screening process. After engineering so many panels to find the best molecules, the protein coming from this plate purification, I used to do all these different assays in order to find the best molecules for manufacturability, okay, or moving forward for later scale up and eventually doing molecular assessment. So this is a screening tool, and the purification is really part of this process, is an integral part of this process to select the best molecules for drug discovery. So on the small scale here, once the molecules are made, sometimes we need more than just a few micrograms to do the assays. This way are the high throughput purification system, which we used to call the high performance magnetic purification system. It can purify to 48 proteins from 30 to 50 mil. And what the system has is this is the first generation system, which will be followed by Deutsch, which is going to describe the new systems which have been upgraded. So this technology was licensed by GenScript from Amgen. Okay, this slide now shows you the critical parts of the magnetic system here, and I probably will not spend too much time on this because everything is very much self-explanatory. So the mechanism here, just to briefly, is that these magnets you see, which are shown by the arrows, are able to move backwards and forward. So when they move backwards, they release the magnetic field. So the beads are now free to separate from the walls of the vessel, and they are able to mix with the buffer. And after that is done, then you get the beads moving forward, and the cannulas you see here will go inside the tubes of the vessels, and the tubes will go inside the falcon tubes and withdraw all the liquid out of there. That's how you do the purification. It's really dispense and aspirate, and the dispense and aspirate. That's the cycle. During that time, the magnets are moving backwards or forward. So this is the general protocol for magnetic purification on this small scale format. I will not spend time because everything is again very straightforward. We use PBS. We have also developed new buffer systems which can give you a more effective cleanup of the beads and remove the host cell proteins. So this is a head-to-head comparison between magnetic purification, which is shown in green, and then we have the blue, which is shown for the ACTA system. This shows you the yields, and we found that actually we have more yields. This is what we have observed, that we get higher yields, almost 10 to 15% in some cases. It goes up to 20% compared to column purification. And this partly due to the amount of protein which is left during handling steps and the filters where a lot of protein may just get lost, okay? So this is also the quality. You can see that the quality of protein purified from magnetic technology were just as similar to that purified from column purification via the ACTA system. Okay, so I'll skip this part because it looks very much like the ones I've shown you before. So now the other alternative also we have shown, and we have a small device which is called the mini magnetic system purification system. This works only with a 6-well block and purifies 6 samples at a time. In this particular case, we started with a large amount of beads in a cell culture, and what we did was to distribute it into this 6 deep well plate after the culture was left out. But most significant in this case, you can do a hybrid purification whereby you can mix non-magnetic cation exchange beads with the magnetic nickel beads. In that process, you'll be able to fish out the nickel beads and leave the cation exchange beads, the anion exchange beads behind. The anion exchanges are added ahead of time to capture any impurities that may be there, so that when the nickel beads come in, you're starting with a much cleaner sample. Okay. So this, we thought that this was a very interesting application, and we found that the purity of the nickel purified beads were much cleaner than those which are purified through steps and the column purification. Okay. And you can see the mass spectrometry of these molecules shows that putting beads into cell cultures or another way or any other medium does not impact on the quality of the product. Plus, beads or beads were added after the cell culture was removed, you can see that the mass spectrometry are very similar. So now, what are these proteins used coming from the medium scale? What we really do is usually these are used for assays, This is assay development, and you can see the workflow over here. I will not again show the instruments. The cells are really grown in the 6-deep well plate and just transferred to the system, and the system does all the purification. So now I'll go to the large scale. This is a 5 to 50 liter WaveBag magnetic purification system. This system was sort of fabricated because the WaveBags have a very awkward shape, and they are very, they are not like a metal or a vessel with very strong walls. So how do you apply magnetic technology on this? So what we do was on the left-hand side, the very first slide shows that we introduced the beads 24 hours before harvest. This was a 25-liter cell culture. And after 12 hours the following day, we just go ahead and apply the magnetic bead, the magnets just under the bag. So you can see the top slide on the second row here is that the beads are still dark before we put the magnets under the bag. And then after that, putting the magnets under the bag, you can see that the bag is starting to clear. It is after that we drain all the cell culture out of the bag, and what is left in the bag are the magnetic beads on the right-hand side. You can see that the beads are attached within the bag, but the magnets are between the platform and the bag, and that's why the beads are immobilized there. After that, the beads are flushed out of the bag. And so you have a reduction in volume in just about 30 minutes. You get rid of the cell culture, get the beads and wash them, and what you have is a pure protein. Okay. So ongoing improvement in this technology involves automation of the magnetic antibody purification, system, so that we can interface it with the actor system in such a way that we can go directly from the crude cell culture to pure protein after the cation exchange. So we are looking for continuous protein purification of magnetic beads through the polishing step on the actor system. And then after that, we have a simple process. But what we are also doing is to develop specific buffers which will be able to interface magnetic bead purification with the cation exchange, and we have already developed a protocol for this. We do this without pH adjustment or sample dilution. The other step is that a lot of people are moving towards single-use stud tanks instead of WaveBags. And this integrated system now, these are these are conical, or they can be conical vessels. So what we are doing now is to throw the beads directly into these reactors. These are bioreactors. And then at the time of harvest, we just open the system and transfer the beads directly into the processing vessels. There is also a possibility of processing the beads within these bioreactors. So the bioreactor will not only grow cells, but it will be able to do the purification. So you reduce cost and cycle time of transfer, of the beads into another vessel. So with all these improvements coming, automation is a big driver here because there is still a lot of hands-on process in this technology. So I'll hand this over now to Jyoti, who will give you some improvement on the second generation small-scale purification systems, which are now going to be fully automated or more semi-automated. Thank you.
Thank you, Dr. Kaluuya. In the next part of today's webinar, we will describe features and benefits of the MagSA, a semi-automatic magnetic purification system that we at GenScript co-developed with Amgen. So for today's presentation, we will start with a discussion of how magnetic beads speed up your purification workflow. We will discuss the features, benefits, and capabilities of the MagSA. We will discuss how magnetic purification with magnetic beads and the MagSA achieves high protein yields and purity. Then we will summarize GenScript's magnetic beads and purification platforms and end with a discussion about how these innovations broadly benefit the field of protein and antibody purification. So the reason for developing the MAG platform of magnetic beads and devices was the realization that we can save a lot of time and labor by using magnetic beads instead of the more traditionally used purification resins. When using purification columns, columns need to be packed and equilibrated before use. Since larger particles can clog the columns, samples need to be cleared first by centrifugation and filtration before loading them onto columns. These steps of centrifugation and filtration take time. Now with magnetic beads, these early steps can be completely bypassed. When using magnetic beads, samples do not need to be cleared with centrifugation and filtration before use. This is because magnetic beads are free-flowing and cells from the culture do not interfere with binding of the target proteins or antibodies with magnetic beads. Also, there's obviously no column packaging step. Instead of sample loading, you have an incubation step where the magnetic beads bind to the target proteins or antibodies and they incubate with that and bind that. This is followed by the washing, elution, and regeneration steps, all of which are automated when using our semi-automatic purification instrument, the MagSA. Therefore, using magnetic beads saves you time and simplifies your protein purification protocol. So looking at our MagSA, this is a semi-automatic purification device that uses magnetic beads. The features that benefit you the most are the time savings. Compared to gravity flow or other robotic chromatography systems, the MagSA shortens the purification time needed. Because it's based on magnetic beads, the system eliminates the need of centrifugation and filtration of samples. The MagSA is further designed to avoid any endotoxin contamination. The instrument is equipped with programs for UV exposure, sodium hydroxide washing, and also has air filters to prevent endotoxin contamination of samples. The MagSA allows for automatic washing and elution steps, which saves you time and labor. So with all of doing this, the MagSA resolves bottlenecks faced by scientists using column-based purification methods, basically which are low speed and low throughput. So in sum, the MagSA saves you time and labor. Now we will discuss the system capabilities of the MagSA. The MagSA allows purification of up to 12 samples at a time. Each of these samples can be between 5 and 50 milliliters in volume. Samples which are contained, for example, in 6-well deep culture plates or standard 50 milliliter tubes can be directly inserted into the instrument. So the same deep well culture plate or 50 ml tube that you might use to grow your cultures, you can directly insert that into the MagSA. So regarding protein recovery and yields, with sample cultures in our lab, we have purified up to 80 milligrams of antibodies or recombinant proteins per 50 milliliter culture using magnetic beads and the MagSA. The actual yields, of course, would depend on expression levels in various cultures. So the typical cycling time for each set of 12 samples is approximately 40 minutes when using default programs. But the instrument is fully programmable and it can accommodate different protocols that you might want to set. Examples of modifications could be addition of washing steps for some samples or changing the volume of washing buffer for some other samples. So in sum, the AMAG assay can accommodate many different types of samples and many types of purification protocols. So protein purification has three key components. One, of course, is the time taken to purify the samples. The other two major factors are sample yield that you recover at the end of your purification and the purity levels of those samples. So as we discussed, using magnetic beads and AMAG assay saves you time. We also performed extensive testing to see if the yields and purity are compared to FPLC-based chromatography systems. We will share those results with you now. So we tested the antibody yield and recovery using hundreds of samples. Some of the data has been shown here. The samples were purified either using GenScript's Protein A resin and an FPLC-based automated chromatography system, shown by the blue line, or using AMAG Protein A protein magnetic beads, coupled with the AMAG assay instrument, shown by the red line. Sample-to-sample variation aside, we saw no significant difference between the yields using either method. We also tested HCP and endotoxin contamination levels and found very low levels of contamination in purified antibodies, which was similar to what we saw with protein A resins. So in general, magnetic beads can achieve the same high yield and purity as purification resins. So for antibody and protein purification, GenScript provides various magnetic beads that you can use with our instrument, the AMAG assay. For antibody purification, depending on the species that your antibodies belong to, you can use protein A, protein G, or both protein A and G magnetic beads. When working with recombinant proteins, for tagged protein purification, GenScript provides nickel-charged magnetic beads, glutathione magnetic beads, and streptavidin magnetic beads to purify recombinant proteins with those tags. For purification using magnetic beads, GenScript provides one-of-a-kind flexible-use magnetic racks, as well as our semi-automatic device, the AMAG SA. Future instruments for high-throughput, fully automatic purification, accepting more samples or larger volumes of samples, are also currently being developed. With these innovations, we have introduced new products that will benefit the overall field of protein purification. So the reason why the AMAG platform is so powerful is because it combines the high binding capacity and high processing speed of magnetic beads with automation for mid to large volume cultures or lysates. The AMAG platform of instruments, starting with AMAG SA, save you time and labor, as well as increase your throughput so you can process so many more samples per day. For example, with AMAG SA, you can process as many as 60 samples in less than 5 hours. We are also consistently developing new and innovative magnetic beads that meet your needs of high protein capture and recovery while providing high purity in all purified samples. The AMAG assay as well as our magnetic beads are available for testing. If interested, please email us at product@genscript.com. Dr. Kaluya and myself will take questions now, but for additional questions, please feel free to email us at any time. With that, I would like to thank you for your time.
Thank you, John and Jyoti. I have a couple of quick announcements before we start the Q&A. A few of you have already submitted questions, so we're going to jump into those. While our presenters are answering your questions, please take a moment to complete the feedback form that appears on the left-hand side of your screen, and please feel free to continue to submit your questions. All right, so over to John and Jyoti. Let's begin our Q&A session. Let's see, the first question that we have here today. Does GenScript have plans to commercialize the magnetic rods for larger L-scale purification?
Hi, so this is Jyoti again. So yes, we actually have plans to commercialize the magnetic rods. You can place an order immediately as a custom order. And if you want to do that, you can email me at jyotik@genscript.com, or you can email our product department at product@genscript.com. We should be officially launching them in the next few months, though.
That's fantastic. And for those of you listening in, the slides from today are available in the resources box to the right-hand side of your screen, where Jyoti's information is also in there as well. So make sure to download that so that you can keep her contact information. All right, great. So the next question we have here, I know that 18 to 24 hours doesn't hurt viability or quality, but do you need that much time for full recovery? And what recovery would you see at 1, 2, 4, 6, 16 hours, etc.? Also, three-parter here, what brand of beads were used for the quality validation studies?
Hi, so this is a question for GenScript again. So no, you don't have to incubate the beads for 18 to 24 hours. That is only for your convenience. If you wanted to set up the binding step the night before, so you did not have to do that in the morning. However, the recovery is not affected, and you would get the same recovery in a few hours of binding. So now whether you bind for 1 hour or 2 hours, that really depends on how much protein you have in your sample. So you would need to determine that empirically. So for low yields, if you have less than 0.1 milligram per ml protein or antibody, so in that situation, longer incubation is better. So 2 hours is generally sufficient. Sometimes you need to go as long as 4 hours to get your proteins out. So it's really the dynamics of how much protein you have in there and the binding capacity of the beads and how clean your samples are to begin with. So you can determine that empirically. For most of our data, we bound them, we do use a binding time of 1 hour. What brand of beads were used for quality validation studies? So for our antibody binding experiments, we used our MagBead protein A magnetic beads.
That's great. Thank you very much, Jyoti. Another question that we have here, just had to check, what is the scalability and commercial viability?
I think this one would be best for John.
Perfect. John, what do you think about this one? Just had to check, what is the scalability and commercial viability? We may have lost John, okay. So maybe we can come back to that one.
Sure.
All right,
I wanted
question.
to add.
Oh, go for it. Yes.
Yes. So I wanted to add. So we so for MagBead, we show the scalability till 50 ml, and as John showed in his slides, they have tested the scalability to up to multiple liters, 50 liters, even maybe more with wave bags. So yes, in case we cannot connect to him, they have tried this technology with larger scales. And as far as the commercial viability is concerned, we're working to make them commercially available.
That's fantastic.
Okay, maybe.
Oh, hi, John.
Maybe I can. Yeah, I'm sorry. This has been a disaster because I also lost the slides during the presentation for a long time. Yeah.
Oh,
so anyway,
no.
now I'm back. Yeah, it was just terrible. I could not follow the presentation. So anyway, I'll go ahead. As far as we can do now, we have a magnetic tank, which actually we are going to test next week. I think it can handle up to almost 1,000 liters. So it is a continuous process where the cells are just flow through with the cell culture and the beads are captured during that process. So on the bench top, we have gone up as far as 50 liters using the spin, bioreactors as well as the wave bags. So in the lab, we can go all the way from 250 mils all the way to around 50 liters of cell culture. Yeah. Now, going back, there was a question of incubating the beads. That will depend on the volume bead ratio. If you have a very large bioreactor and you put in the beads, in order to capture so much protein in a very short amount of time, you'd have to put in a lot of beads. So that's why the 18-24-hour process was, introduced, because normally the capacity of the bead is very high, but if the volume is very large, you need enough time to have that equilibrium so that you can capture the beads in the bioreactor.
That's great. Thank you, John, for that answer. That was great. So we have another question here. What is the lowest concentration, however, you have managed to get enough recovery?
Okay, I've done a lot of studies in the range of protein concentration or expression levels. The lowest I've gone to is about probably 0.1 mg per liter. Okay, that's how low I've gone, and I've been able to recover, or we could recover out of there. The challenge here is that you tend to get a lot of non-specific binding because a lot of your proteinase sites are just open for grab for anything in there. So when your yields are very low, it means the purification is going to be more challenging. So we have introduced new buffers which can give you very good selectivity in terms of purification. And in this case, we tend to do the washing at 2 different pHs. The lower pH allows you to reduce non-specific binding because you're very close to the elution point, whereby most of the non-specifics are going to just get removed off the beads before you elute your protein. The alkaline pH allows you to remove any proteins which bind based on some, ionic effects. So you can do it in both ways. Both are really removing non-ionic interactions as well as hydrophobic. So alkaline pH around pH 8.5 and acidic pH is around pH 5.
That's great. Thank you, John. We have another question here. I've been testing out GenScript's magnetic beads recently using standard buffers for a typical antibody workflow. Do you have any recommendations to reduce bead clumping?
Yes, so you can reduce magnetic bead clumping by adding Triton X or Tween 80 into your PBS during the initial wash step.
Perfect. Thank you, Jyoti. Another question we have, what is the minimal affinity need for using Mag assay systems specifically for non-FC tag protein targets?
So I'm going to have to get back to you on that. We'll keep this question and we'll answer that later.
That's perfect. Okay. Another question we have, is it correct to say MagBeads are more suited for screening stage of protein purification?
Is that towards me or to Jyoti?
I think, John, you can answer that.
Okay, so I can go ahead. So the question is about what? Sorry, if you can repeat the question.
Sure. Is it correct to say MagBeads are more suited for screening stage of protein purification?
No, you can use it in both. In fact, our laboratory now is switching our platform. We're getting rid of centrifuges in general. We're trying to get rid of centrifuges because of space and the time it takes. Purification using magnetic beads is now becoming mainstream. And so you can use it in both. I think in both cases the platform works perfect. But to scale up, we find it even more exciting to use them at a larger scale because of the cycle time you reduce. And now the people who are doing expression are becoming protein purifiers. And the technology has brought them into mainstream, that they can now express proteins and purify them even in the bioreactors.
Great. Thank you, John. Another question we have. Thank you for your presentation. The device looks good. Do you have an idea on elution volume?
Yes, so in our device currently, we recommend a minimum of 2 ml elution volume. You can go as low as 1 ml depending on the starting volume of magnetic beads.
Yeah, I could chime in here because I've been addressing this question. One of the big challenges with the magnetic bead has been trying to reduce the elution volume. The tendency is that because you're doing it batch-wise, you tend to repeat a number of elutions and so on and so on. So I've developed some some elution buffers which can allow you to elute these proteins in extremely very high concentration and a very low volume. One elution step and all the protein comes off the beads. So the bead volume ratio is no longer a big factor now.
Great, thank you, both of you. Another question, what's the typical elute concentration after a mag prep? Is it necessary for further concentrating the samples?
Jyoti, do you want to answer, or I can, based on your experience there?
You can go ahead, John.
Okay, so with these new buffers now, we can go up to 6 mg per mil, and in some cases we've gone as high as 22 mg per mil in very large scale. So everything is all about buffers. What buffer you're going to use and at what pH is going to determine. We are eluting the protein around pH 2.7, 2.8, but we have added stabilizers to avoid the protein from facing very harsh conditions of the acid, So there are sort of co-solubilizers and the modifiers which are which are protecting the sample in this acidic environment, and that allows us to go extremely low pH. And we don't titrate the protein. The protein can sit in these solutions for weeks at least without any aggregation changes. So it goes back to the elution buffer here and the pH, of course.
Okay, great. Thank you, John. Next question. Will the system be available for testing in the EU anytime soon?
Yes, so we're planning to do some testing in EU, starting with Switzerland and the UK in January. So if you're interested in testing the system, you can email me and let me know so we can add you to our list.
Fantastic. We have a couple of questions in here just asking the same thing. So I guess I will ask you both. How many times can you repeat using the same batch of beads, or can you reuse beads?
Okay, I can go first based on my experience. The beads have really evolved. The first series of beads have been working with GenScript on their bead production. The quality and the capacity has really changed over time, and the stability of the ligand to the beads has really improved over time. Currently, we have gone as far as around 30 cycles, and we see around 28, 30, you start to lose around 10 to 15% probably. So you can reuse these beads for a very long time. The challenge, of course, is trying to after using the beads, there is a tendency to mix them up and lose them. So you really need to catalog and stay with the same beads for a very long time. And when you have a big laboratory, there is a lot of mix-up that is very hard to track. So you need a tracking system. We are using a barcoded system so that we know which beads we're using at what time. Yeah, Jyoti, I don't know whether you want to add in.
Yes, so I wanted to add to this that the reusability really depends on how much you can clean the beads, how well you can clean the beads. So our MAG protein A magnetic beads, you can wash them with sodium hydroxide. That's why you can reuse them so many times. In our lab, we're able to use them 40 times, reuse them 40 times, for example. However, not all ligands are as good as our recombinant protein A. So for example, protein G magnetic beads or nickel charged magnetic beads, you would not be able to reuse them that many times because you cannot wash them with sodium hydroxide. In the case of nickel charged beads, for example, if you wash with sodium hydroxide, then you'll need to recharge them with nickel sulfate to add the nickel back to the beads. So yeah, it really depends on what protein you're using and what magnetic beads that you're using. Yeah, thank you.
Okay, maybe I could follow up. I could follow up on this, on washing the beads. This is very critical because you get a lot of host cell proteins, endotoxins, and so on. What we found is that when you recycle between acidic and the alkaline pH, you tend to get a much cleaner cycle without exposing the beads to extreme pH over a long period of time. So we start with a phosphoric acid, then you go to an alkaline, and you give it a very short cycles, probably 5 minutes each. And you go back analyzing, you find that most of the protein and the endotoxins are gone.
Great. Oh, perfect. Thank you, John. So next question I have here, what is the binding capacity for the MagBeads?
So the magnetic beads binding capacity depends on which magnetic beads we're speaking about. So for the MAG protein A magnetic beads, the binding capacity is approximately 40 milligrams antibody per milliliter settled beads. For our nickel charged magnetic beads, it's about 20 milligram of recombinant histidine tagged protein per ml settled beads. So it depends on the beads. And I can refer this to John as well, and he can share his experience with binding capacity.
Okay, I've worked with a number of beads out there. There are also other suppliers who are making some of these beads. I think the market is getting quite busy because of the big interest out there. The capacity varies depending where you are getting the beads from. But the beads were used from a GenScript. I think we have done a detailed studies and we found that the capacity has gone around the 70 to 80 mgs, their top line of the beads. They go very close around 70 mgs per mil, 60 to 70 mgs per mil. So those are the beads we're using in our lab. So you don't need a whole lot of beads to bind your protein or to get your recoveries from the cell culture. Moreover, we also find that the fewer beads you have, the faster it is to do the washing and the elution and so on. So the more beads, it means you are going to do more wash cycles and so on.
Great. Thank you both for that. Another question, what is the protocol for stripping and reusing the Ni+ beads? Is a protocol available?
So we can send you the protocol for a regeneration of beads, yes. It's available.
Great. So you guys will follow up on that one. Fantastic. Let's see. At what concentration for the detergent? This is a follow-up to the bead clumping question.
Yes, so we recommend 0.05% of tween 80.
Great. Let's see. Another question we have, is it cost effective to use magnetic beads?
Yes, I think John would be the best person to answer that.
I thought you should answer that. Okay, anyway, yeah. Cost effective, yes. Cycle time, FTEs, number of people doing the work. The beads are still very expensive on the market. There is no doubt about it. And the price, I don't want to talk about price because I don't sell them. I just buy them. Okay? So for that reason, I leave the cost different. But when you add in the amount of time and also the filters you'll be using and the centrifuges and how long it takes you to process your sample, we have added the work and we have been deciding should we stay on magnetic beads or stay with the centrifuges. We find that actually now one person can use magnetic beads all the way from expression to purifying a protein in a place where we're using we needed at least 2 to 3 people on a large scale. One person can process the whole sample in just about one day. So we find that
in this era where we have to find drugs in a very short cycle time, reduce cost, when we add all the cost of having 2 FTs or 3 FTs, everything just adds up to going for magnetic beads. And I feel that the prices will start to drop as more players come into the process, as more people start to participate in the game here.
Great. Thank you. Let's see. Another question here. How many beads are in a milliliter, and does it matter?
Jyoti, do you want to reply or sure?
Yeah. No, from GenScript, when we supply beads, they are 25%. So 25% settled beads is the concentration that we supply them at, and different vendors supply different concentrations.
Yeah, then maybe I could add here the physical property of the bead itself. Beads with a smaller diameter, smaller spherical diameter, say 25 to 30 microns, tend to bear a high capacity of protein A, for example, a ligand. The bigger the bead, the less ligand you are going to have on. So if you have 1 mil of beads with a smaller diameter, you'll have a lot of beads in there. It means you have a lot of high binding capacity in those beads.
Great. Thank you both. This question is addressed to John. So John, could you elaborate on how to optimize the elution buffers?
Optimize in what sense? In a volume, or optimize in terms of eluting the protein off, or in one step? I guess that is very hard to follow up. So I will address both anyway in one question. Yeah. Okay.
Absolutely.
Optimizing the elution has evolved with a process I've been working on for the last 4 years. That's when I started magnetic beads. The elution with the conventional buffers they use usually is about trisglycine or sodium acetate. They are okay, but they don't seem to work as well as the buffers we have developed lately. And part of it is that those buffers are prone to aggregating proteins. They have a tendency to aggregate your proteins. So what I've done is to use, and this is still under, patent, so I cannot say much about it, but we're using mixtures of acids and osmotropic reagents, and that mixture is able to give us extremely low pH without denaturing the proteins. And therefore, those mixtures actually can go as far as low as 2.5, 2.4, and the lower you go in these elutions, the lower the elution volume is going to be. So when you go with the buffers, which tend to be very difficult to elute protein off, then you are going to end up with larger volumes because you are constantly going through different cycles of extraction, and you end up with liters of extract. Okay, so the whole story is about the buffers, and that's what I was talking about. Now, in terms of elution volume, of course, will depend again on the buffer composition you are using and the pH. Very low pH, stabilized elutions will give you the best conditions, and we'll be publishing this once the patent is completed.
Great. Thank you so much, John and Jyoti, for an outstanding presentation. Unfortunately, we have run out of time, so thank you once again to John and Jyoti, and also to our sponsor, GenScript. If anyone submitted a question that wasn't addressed, please keep in mind that the speakers will reach out to you directly, as we said during this Q&A. This session was recorded. They'll receive a notification in 24 hours when the on-demand session is available for viewing. Before you log off, please take a moment to complete the feedback form so we can continue to improve your webinar experience. Thank you very much, and have a very productive remainder of your day.